All right, so in the first part of this section, we dealt with the product rule, which is our technique for taking derivatives of products of functions. So naturally, we're now going to move on to the quotient rule. And based on what we saw in the first part of this, as you might now expect, the derivative of a quotient doesn't necessarily work the way you might think it would work. So the derivative of f of x over g of x is not equal to f prime over g prime. It doesn't just distribute the differential operator to the numerator denominator, even though with limits that does normally work. So instead what we're going to do is walk through, again, a proof of this thing that we call the quotient rule. And yes, this is going to look very complicated and involved. We're going to talk through it, but for you, the most important thing is to see this proof, hopefully understand the logic behind it, but then just be able to use the quotient rule afterwards. So our goal is to take the derivative of f of x over g of x, where once again we assume that f of x and g of x are both differentiable functions, and go straight to the limit of our derivative. So the definition of our derivative. The definition would say that this is equal to the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. Now I'm going to use a similar approach here as I did with the product rule. I'm going to be adding and subtracting the same quantity away, but I'm not ready to do that yet because the first thing I want to do is clear out these smaller denominators. So what's going on from here to here is I'm multiplying, and I'll even write this step in, I'm multiplying by g of x times g of x plus h over g of x times g of x plus h, because that would be the least common denominator for these two guys up here. You can see that the g of x would cancel this denominator, leaving me, g of x plus h would cancel this denominator, leaving me with a g of x times an f of x plus h here. And then similarly, after the cancellation that happens here, I'm going to have minus f of x times g of x plus h left over from this term. My denominator is just going to look like h times g of x plus h, okay? Here's where I add something and then subtract it. So these terms here, my first and last terms in my numerator in this step, match these two terms up here. And in between, I'm going to be subtracting f of x g of x and then adding the same thing back, f of x g of x, so that these would cancel out and get me back to this step, showing that these two things are equal to each other. And again, my point or my purpose for doing that is to be able to group up these first two terms, factor something out, group up these second two terms, and then factor something out in such a way that the result leaves me with difference quotients, because that's how I'm going to turn things into derivatives. But I'm also doing another step as I get from here to here. You notice that the h that's in the denominator down here is missing down here, but it's showing up here and here. So what I'm actually doing is I'm multiplying this by 1 over h over 1 over h. This 1 over h in my denominator is going to cancel this h out. And this 1 over h would put everything over an h. It's turning everything in my numerator into quotients. Okay? Now, in addition to that, my first two terms here both have a common factor of g of x. Notice that gets factored out completely. And here, these each have a factor of f of x in them, but I'm actually going to be factoring a negative f of x out. See how I have a negative f of x? And what that does is it leaves me with this positive g of x plus h and a negative g of x here, which I can then switch the order of those terms. I see I have a typo here. These should both be g's. G and G there. So now I have a difference quotient for my f and a difference quotient for my g. Okay, and you can see the f of x that was factored out here. So now I would do what I did before and apply a limit law that allows me to bring the limit into the numerator and denominator of my quotient, and then kind of bring that limit into each factor of each product appearing up here. So there's a whole bunch of limits now that are all appearing up here. Two of these limits become derivatives because I have a limit as h approaches 0 of this difference quotient. That becomes f prime of x. Similarly, this difference quotient, after applying the limit, becomes g prime of x. And then just like in the proof of the product rule, the limit as h approaches 0 of f of x would just be f of x because this is being treated like a constant since there's no h appearing in there. And then this guy right here, same thing. The limit as h approaches 0 of g of x would just be g of x. So you can see my numerator kind of resembles the product rule, except I have subtraction instead of addition, and the order of these terms appears to be reversed. In my denominator, I'm also taking the limit as g of x, as h goes to 0 of g of x times g of x plus h. And using the same logic as the proof of the product rule, because g is differentiable, we know that it's also continuous, and we show that that implies that the limit as h approaches 0 of g of x plus h is simply g of x. So this entire denominator goes to g of x times g of x, or g of x squared, okay? And this thing right here is my quotient rule. Here it is stated again as it is in your book using differential operator notation, although this makes everything look much more complicated. Using my UV notation instead, it's still a relatively complicated looking formula, but much simpler in appearance than the previous two presentations of it. So if we let u equal f of x and v equals g of x, so in other words, u is my top function, v is my bottom function, then what we're seeing up here is that I should have the bottom function times the derivative of the top, or vu prime, minus the top function times the derivative of the bottom, uv prime, and then my bottom function gets squared, so v squared. Now, I mentioned in the product rule, let me go back to the product rule really quick. When we stated our product rule here, I said that you could do this in either order. I could do uv prime plus vu prime, or I could do vu prime plus uv prime, because addition is commutative. I could switch the order, and nothing actually changes about that. We don't have that luxury with the quotient rule because we have subtraction instead of addition. Subtraction is not commutative. You have to make sure you're subtracting in the correct order. So when you're doing the quotient rule, it's much more important that you remember exactly what this formula looks like and only use it the way that it looks like. So vu prime minus uv prime. You don't want to switch these two because then you'll get the opposite of the correct answer. So here's an example of a quotient that we would like to differentiate using our quotient rule. So this is a polynomial over another polynomial, and what I'm looking to do here is apply my quotient rule, which says start with vu prime, or bottom function times the derivative of my top function. My bottom function is x squared plus 3. My top function, this quadratic polynomial, if I differentiate that, I'm going to use my power rule where I can, so this 3x squared becomes 6x. Minus x, its derivative would be negative 1, and then that constant goes to 0, and I'm left with this, okay? Minus uv prime, so minus my top function, 3x squared minus x plus 1 times my the derivative of my bottom function. The derivative of x squared plus 3 is just 2x. All over my denominator squared, x squared plus 3 squared. Okay? I had mentioned before in the previous video that I typically will try and factor things where I can for the purpose of simplifying this derivative and ultimately, setting it equal to 0 and solving that in some of the problems that require that. For this one, I'm going to leave this alone for now, but that's only because when I multiply all of this out, the end result is not going to be something that factors terribly nicely, and so I'm not going to be able to get that far with it. But hopefully this illustrates how we apply the quotient rule. So let's move on. This is our last page here. A couple more examples. Here's another function that I would like to take a derivative of, and you'll notice it is a quotient, But because the quotient rule is a little bit involved, there's a lot more to do there. It's sometimes good to look at a function like this and first ask, can I simplify it in a way that makes the derivative easier to compute? Now this thing right here is, because I only have an x in the denominator, I can simplify this first. Notice y is the way that I have this written. This is the same thing as 5x squared minus 4x plus 2 plus 8x to the negative 1 power. Okay? Hopefully you can see what I did getting from here to here. I did a straightforward algebraic simplification. But now that I've done that, the result no longer looks like a quotient. It looks like a sum and difference of power functions as well as a constant function here, which are much easier to deal with. So taking the derivative now, y prime is just going to equal 10x minus 4 minus 8x to the negative second power. Notice I was able to do that much more quickly by simplifying first. You can't always do that. So in the previous example, my denominator was not just, an x or x to some power. It was a quadratic with a couple of terms. I wasn't able to simplify this one the way I was this one. So you have to kind of intentionally be on the lookout for that kind of a simplification, and it makes the whole process far easier. Let's take a look at another one. I want to find the equation of the tangent line to the curve y equals x squared minus x plus 3 over e to the x at this point here, 0, 3, which you could verify this point would be on this curve. I can't simplify this one the same way I did before because I have an exponential function down here. It's not going to simplify in the same way. So the product rule is appropriate here. I'm sorry, quotient rule, I should say. The quotient rule is appropriate. Y prime is going to equal the v u prime, so v is e to the x, u prime, so that's the derivative of my numerator, which using my power rule would be 2x minus 1, minus v u prime. So I'm going to put u prime first. The derivative of, uv prime. So the derivative of v, my denominator, is e to the x. Remember, e to the x is its own derivative, times my numerator, which is x squared minus x plus 3, all over e to the x squared. Okay? Now notice, even though, again, I could leave this in this form, I have an e to the x showing up in both of these terms, which could be factored out. And then in addition to that, that e to the x could be canceled with one of these e to the x's. So I'm going to do this, okay? That means that y prime is equal to, let's simplify my numerator. If I distribute that negative in, I'm going to have negative x squared. I'm going to have negative x, so that's plus x plus 2x, that would be plus 3x. And then I'm going to have negative 3, also minus 1 here, which makes negative 4, all over e to the x, okay? And then I could, if I wanted to, I could go through some steps of simplifying this, see if I could factor my numerator, which maybe I could, maybe I couldn't. But I'm not going to bother with that because what it's saying here is that I'm looking for the equation of the tangent line to this curve at a specific point. And the x-coordinate of this point is 0. So I know that the slope of the tangent line I'm looking for is whatever I would get from plugging 0 into this function. Okay? So I need to now evaluate this at 0. I'm going to change my notation up here. dy dx evaluated at x equals 0. Remember, that's what that notation means. Is equal to, well, if I plug zeros in here, I'm going to get 0 plus 0 minus 4, so negative 4. Over e to the power of 0 is 1. So this is equal to negative 4. Finally, I could find the equation of my tangent line. Y minus 3 equals negative 4 times x minus 0, which I'm seeing up there, or better to write it this way probably. I could simplify it pretty easily. Y equals negative 4x plus 3. Okay? Pretty straightforward, but the thing here was using the quotient rule to get the derivative in the first place. All right, my last example I want to do is a word problem because it's important to get practice with these as well. So this is it's a problem involving manufacturing and pricing. So when I teach business calculus, this is the type of problem that we do a whole lot of. It says a manufacturer produces bolts of fabric with a fixed width. The quantity Q of this fabric, which we measure in yards, that is sold is a function of the selling price P, which is given in dollars per yard. Okay, now I want to stop for a second to think about this. This is kind of basic economics. If you understand supply and demand and things like that, this isn't specifically supply and demand, but as you would expect, if you raise a price on a particular product to some absurd level, you're likely to sell very little of that product because people don't want to pay that much for it. If you lower the price, you would expect more people to be willing to pay for that product, and so you would expect to be getting a higher sales for that. Now that relationship's not necessarily linear, but you do expect those two things to be related. The amount that you sell makes sense that it would be related to what you are charging for that product. And so what we're saying here is that Q, our quantity sold, is equal to some function of P. It's equal to some function of the price per unit, okay? Now the total revenue that you earn selling at a price of P, which we call capital R of P, would be equal to P times F of P. And hopefully it's obvious why this is true. You sell something for a certain price per unit, and if F of P or Q represents the number of units sold, then the price per unit times the number of units sold is your total revenue, how much money you make from those sales. That's what this is saying, okay? So there's two parts to this. What does it mean to say that F of 20 equals 10,000 and F prime of 20 equals negative 350? So starting with the first one, F of 20 equals 10,000. What does that mean? Well, again, F is a function that was defined up here. F of P is equal to Q, where Q is the quantity of fabric sold in yards, and P is the price per unit, or specifically price in dollars per yard. That's the unit that we're using. So this is $20 per yard, and this is 10,000 yards. So the function here tells me that this means that 10,000 yards are sold when priced at $20 per yard. Whoops, I don't know why I did a D, yard. That's literally what that means, okay? But then we have F prime of 20 equals negative 350. What does that mean? Well, remember, the derivative represents a rate of change. And what would this rate of change be measured in? First of all, it's helpful to look at units first. So the output of this function Q is quantity of fabric sold, and the input for this function P is selling price in dollars per yard. So the units here would be quantity of fabric sold, yards sold, per dollar per yard. That's how we would interpret that rate. So what this means, though, is if we price this fabric at $20 per yard, the negative rate of change that we're getting out of this indicates that our sales are dropping as this price changes. So what does this mean? When priced at $20 per yard, sales of fabric are decreasing at a rate of 350 yards per dollar per yard. Okay? Now that might seem a little bit weird because we use the word per twice, but the reason this is necessary is because one of our quantities here is measured in dollars per yard, whereas the other one is simply measured in yards. So the rate of change that we're talking about here would have units of yards per dollars per yard. Okay, now notice I didn't write negative 350 here because I'm using the negative to interpret this as a decreasing rate of change as opposed to an increasing rate of change. And if you think about this from the perspective of the manufacturer, this suggests that you would probably want to lower your price. Maybe there's more analysis that would need to go into it, but because the price is $20 per yard and we're seeing a negative rate of change there, we have a decreasing trend in our sales if at this price point here. So we might want to lower our price to try and get an increasing trend in our sales. But there's a kind of a balancing act there too. If you lower your price too much, even with a lot of sales, you may still be making less revenue overall. So that's where there's a little bit of subtlety to this. So let's go to part B. Assuming the values from part A, so these quantities here, we want to evaluate r prime of 20 and interpret our answer. So let's start with r prime of x first of all. Because r is defined, r prime of p. X is not the variable, p is the variable. It's defined as a product of two functions, one where we can see explicitly what that function looks like, p, the other one we don't have a representation of. We're going to be using our product rule. R prime is equal to the first times the derivative of the second, so p times f prime of p, plus the derivative of the first times the second. The derivative of p is just 1 times f of p. That's just going to look like f of p. So that's straight from my product rule. Now, this would imply that r prime of 20 is equal to 20 times f prime of 20. I'm plugging 20 in for the p's here, plus f of 20. Or 20 times f prime, we said f prime was equal to negative 350. Plus f of 20 was 10,000. Okay. 20 times negative 350 would be negative 7,000. Plus 10,000 here. And this would be equal to 3,000. Revenue is measured in dollars. Okay. In this little bit of space right here, I'm going to write my interpretation. I didn't leave myself a ton of space. So what this means is that at $20 per yard, our revenue is changing at a rate of $300. $300. What would the revenue be measured in, I should say? Revenue is measured in dollars, and P, its independent variable, again, is measured in dollars per yard. So I would measure this in dollars per yard. Okay? Now this rate of change is positive, so we're actually seeing an increasing rate of change in our revenue, even though we're seeing a decreasing rate of change in our number of sales. So what this sort of implies for us is that we may not want to drop the price like we initially assumed in part A, because even though we're seeing a decreasing rate of change in our sales, the price is high enough that it sort of overcomes that, and we're still seeing a positive rate of change in our revenue. When our revenue's rate of change starts to become negative, that's when we think of that as losing money in the long term. So this means when priced at $20 per yard, our revenue is increasing at a rate of $3,000 per yard. In fact, what this suggests is that we might even want to increase the price a little bit more, because we're seeing an increasing trend here as we change our independent variable of dollars per yard. So if we increase that even more, we may still continue to have that increasing trend. Okay, so that's going to wrap up section 3.2.